Why do financial returns often look calm for weeks and then suddenly turn turbulent? The direction of each return may remain hard to predict, yet the size of the moves is clearly persistent. Large changes up or down tend to be followed by more large changes, while small changes cluster together. This is volatility clustering. It motivates the ARCH model, our first framework, for allowing conditional risk to change over time. The conditional mean and the conditional variance answer different questions. The conditional mean is our best forecast of the level of a variable, given information available yesterday. The conditional variance measures the uncertainty around that forecast. An autoregressive moving average model may describe predictable movements in the mean, while a volatility model describes predictable movements in the variance. A high variance forecast means a wider distribution of plausible outcomes, including both gains and losses. It does not forecast a market decline. Confusing volatility with direction can turn a sound risk model into a misleading trading claim. Any directional forecast must come from the conditional mean or another explicitly modeled feature. The conditional distribution also matters for risk. If standardized innovations are assumed normal, the fitted variance determines a conditional normal density. Financial residuals often have heavier tails, so a normal ARCH model can understate extreme loss probabilities even when its variance recursion is useful. Comparing normal and heavy-tailed innovations separates a scale model from a distributional assumption. IRCH creates nonlinear dependence that ordinary autocorrelation can miss. The raw shocks can be serially uncorrelated, while their squares and absolute values remain predictable. This is why a white noise conclusion for returns does not end the analysis. Diagnostics should examine the transformations linked to the economic target, especially squared residuals for variance and tail indicators for extreme risk. The central lesson is that unpredictability in levels does not imply unpredictability in risk. ARCH converts the visible clustering of large and small movements into a conditional variance forecast based on past squared shocks. Its strengths are transparency and direct interpretation. Its main limitation is that long persistence may require many lags. That limitation leads naturally to Garch, which summarizes a long history of shocks through a much more parsimonious recursion. We ended the last lesson with a problem. An ARCH model may need many lagged squares just to reproduce slowly decaying volatility. Let me show you how the generalized ARCH model, or Garch model, fixes this by adding lagged conditional variance. In a Garch 1-1 model, today's conditional variance equals an intercept plus alpha times yesterday's squared shock plus beta times yesterday's conditional variance. Alpha measures the immediate reaction to new information. Beta carries past volatility forward. Together they give us persistent but parsimonious risk dynamics. The general Garch model can include P lags of squared shocks and Q lags of conditional variance. In practice, Garch 1-1 is often a strong baseline because it uses only 3 variance parameters. The intercept sets the long-run scale. The ARCH coefficient controls how sharply volatility reacts to fresh news. The Garch coefficient controls how slowly the effect fades. A high beta does not by itself imply a large response to news. Persistence and impact are different features. To keep the conditional variance positive in the standard specification, the intercept is positive, and the shock and variance coefficients are non-negative. For a weekly stationary Garch 1-1 process, alpha plus beta must be below 1. The unconditional variance then equals the intercept divided by the quantity 1 minus alpha minus beta. When the sum is close to 1, volatility is highly persistent, and the long-run variance becomes very sensitive to small estimation errors. Repeated substitution reveals why Garch is parsimonious. Today's variance can be written as a constant plus an infinite sequence of past squared shocks. The weights decline geometrically at rate beta. Thus, Garch 1-1 behaves like an infinite-order arch model whose lag pattern is smooth rather than freely estimated. A recent shock receives weight alpha, the preceding shock receives alpha times beta, and older shocks receive progressively smaller weights. This structured decay saves parameters and stabilizes estimation. Weak stationarity concerns constant first and second moments and covariances that depend only on distance in time. For a general Garch model, a finite unconditional variance requires the sum of all arch coefficients and all Garch coefficients to be below 1. This condition is easy to interpret, but it is a moment condition. It should not be confused with the broader question of whether the full probability distribution is invariant over time. For Garch 1-1, strict stationarity is governed by the average logarithmic growth of the random coefficient beta plus alpha times the squared standardized innovation. The required expected logarithm must be negative. This condition can hold even when alpha plus beta is at least 1. In that case, the process may have a stable time invariant distribution, but no finite unconditional variance. Strict stationarity does not automatically deliver weak stationarity or finite moments. This distinction also helps explain heavy tails. A Garch process can produce a stationary distribution with far more probability in the tails than the innovation distribution alone would suggest.